It's something we do a dozen times a day without even thinking about it, right? You flip a switch and boom, light. It feels like magic. But what is actually happening inside the wall? Well, it's this incredible story of invisible forces, and that's exactly what we're going to dive into.
Seriously, have you ever really stopped to think about it? What's going on in there? You flick that little plastic switch, and suddenly the room isn't dark anymore. But it's not magic, not at all. There's a really cool process happening inside those wires, so let's get a closer look. Okay, so to really get what's happening, just staring at the wire isn't going to cut it. We need to go smaller. I mean, way smaller. We're going to zoom all the way in, right down to the atomic level, because that's where the real story starts. All right, so our journey starts with the absolute star of the show, the tiny, tiny particle that makes this whole thing work, the electron. So basically everything, I'm talking the walls, the wire, even you and me, is made of zillions of atoms. The easiest way to picture them is like tiny little solar systems. You have a heavy center, that's the nucleus, and then you have these even tinier particles just zipping around it. And those are our key players, the electrons. They're these tiny orbiting particles, and here's the important part. They have a negative charge. That one little detail, it's the key to, well, everything we're about to talk about. Okay, so we've got all these electrons just kind of hanging out in their atoms. So what? How do we get from that to a light bulb turning on? How do we get them to move? Well, that, my friends, is where electricity comes into the picture. So let's imagine a normal copper wire. To us, it just looks like a solid piece of metal. But if you could see it at the atomic level, it's more like a superhighway just jam-packed with electrons. They're all part of the copper atoms, and they're just waiting for a signal, a reason to start moving. And that's where something like a battery comes in. The moment you flip that switch, you complete the circuit. And what the battery does is give all those electrons a little push. It's the motivation they need to stop lazing around and start moving, all in the same direction. And what happens next is this amazing chain reaction. One electron hops to the next atom, which pushes another electron out, and so on, creating this continuous stream. This flow gets funneled through the light bulb's super thin filament. It gets so crowded in there that the filament heats up a lot until it glows. And there you have it, light. So that's really all electricity is. It's just the movement of electrons through something like a wire. The whole river of charge idea, it's a perfect analogy. It's just this constant flowing current. Okay, that makes sense, right? But it brings up another question. If it's the same river of electrons flowing through the wires, why is a 100-watt light bulb so much brighter than, say, a 60-watt bulb? What's the deal with that? Well, the answer comes down to two really important words that, honestly, a lot of people mix up all the time: power and energy. And trust me, understanding the difference is going to make your electricity bill make a lot more sense. All right, so let's put our two bulbs side by side. You've got the 100-watt bulb, and it's super bright. Then you have the 60-watt one, and yeah, it's definitely dimmer. They're both hooked up to the same electrical river, so what gives? The difference is power. And we measure that in watts, which you've definitely seen on light bulbs. Now, here's the thing. Power isn't about how much electricity you're using. It's about how fast you're using it. The 100-watt bulb is so bright because it's just chugging down energy way faster than the 60-watt bulb. It's literally more powerful. So if power is the speed, what's energy? Well, energy is the total amount of electricity you use over time. It's the fuel that power is burning through. So a high-power device, it's going to need a lot of that fuel to keep running. If that still sounds a little fuzzy, don't worry. I've got a super simple analogy that's going to make this crystal clear. It all comes down to a car. Okay, so let's connect this to a car, something we all get. In this analogy, power is your car's speed, miles per hour. And energy, that's the fuel you actually use on your trip, measured in gallons. Think about it. A race car flooring it at 150 miles per hour has incredibly high power. But a minivan on a cross-country road trip, even if it's going slow, is going to use a whole lot more total energy, right? A lot more gallons of gas. Our bright 100-watt bulb is just like that race car. It's high power, so it burns through its fuel, its energy, super, super fast. So let's just boil it down to the absolute basics. Power is how fast. Energy is how much. That's it. That's the whole difference right there. All right, so let's wrap this up with a question you can actually use. That electricity bill you get every month, what do you think they're charging you for? Is it for your power, how fast you used electricity? Or is it for your energy, the total amount you used all month long? After this, you know exactly what the